This is 2016 AP Calculus BC Free Response Question 1. In this video, I will show you how to solve Part A and Part B. In this case, we have 4 parts. I'm going to have another video for Part C and D. Let's look at the question. Water is pumped into a tank at a rate modeled by W of t is 2000 e to the negative t squared over 20. So that's the rate the water is pumped into a tank from 0 to 8, where t is measured in hours. And water is removed, in this case this thing is removed from the tank at a rate modeled by R of t liters per hour, where R is differentiable and decreasing from 0 to 8. And we have the selected values of R in the table above. At time t equals 0, there are 50,000 liters of water in the tank. Now let's look at A. Estimate R prime of 2. We have to estimate R prime of 2. Well, R prime of 2 is the instantaneous. It's the instantaneous slope. Instantaneous slope or instantaneous rate of change of R, of the graph of R at 2. How can we estimate this? Now, if you think about it, let's say our graph of R, we know it's decreasing, so let's say it's doing something like this. You want to find the instantaneous slope when time is 2. At this point, the slope is going to be the slope of the tangent line, so it's going to be the slope of this line. The way we can approximate this is by finding two values close to 2, which we know the y value of, and using it to calculate the slope of the secant line. Obviously, the slope of this line is not going to be the same as the slope of the actual tangent line, but it should give a pretty good approximation. In this case, we know the value of R at 1, and we know the value of R at 3. So in this case, we can use this point and this point, where this point is when t is 1 and this point is when t is 3, to approximate the instantaneous slope at 2, which is going to be R of 3 minus R of 1 over 3 minus 1. This is average. This is average rate of change, or the average slope. That's the average slope. That's the average slope from 1 to 3. This should give you an approximation of R prime of 2. Now, what is this? Well, R of 3 is 950 and R of 1 is 1190. So it's 950 minus 1190 over 3 minus 1 or 2, also known as what does that come out to be? 240, negative 240 over 2, or negative 120. In this case, it says indicate units with measures, so make sure you put down the units. So it's going to be 100, negative 120. What's the unit going to be? Well, R of t is in liters per hour, and the time is in hour, and we're finding the rate of change of R of t with respect to time. So in this case, the unit is going to be liters per hour, or negative 120 liters per hour squared. That's going to be our answer. Now let's look at B. Use a left Riemann sum with the 4 subintervals indicated by the table. It's the left Riemann sum to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or an underestimate? Give a reason for your answer. Well, the first thing you have to realize is because R of t is the rate at which the water is removed from the tank. The definite integral of R of t from time equals 0 to time equals 8 should give you the amount of water removed. Now, why is that? What's the definite integral from something to something? Well, that's going to be the antiderivative. It's going to be the change in the antiderivative of R from time equals 0 to time equals 8. In this case, because R is the rate at which the water is removed from the tank, the antiderivative is the amount of water removed from the tank. And this thing is going to give you the change in that amount of water, or it's going to give you the amount of water removed. Now, what's this in this case? Now, let's say R of t is doing something like this. We know R of t is decreasing, so we know it has to go down. So let's say that's something it's doing. And we want to approximate this using the left Riemann sum. Now we know R of t's value when time is 0, when time is 1, when time is 3, when time is 6, and when time is 8. 0, 1, 3, 6, 8, 0, 1, 3, 6, and 8. So we know the R of t's value at each of these points. So what we can do is we can use the left Riemann sum, which means we are using the left endpoint of the interval for the height. If we use right Riemann sum, we're going to use the right endpoint, which is going to give us this green rectangle. But in this case, we are using the blue rectangle whose height is given by the left endpoint. So we are adding these rectangles up, whose heights are given by the left endpoint. So what's this going to be? The definite integral from 0 to 8 of R of t dt is going to be about, in this case, the area of this rectangle is going to be 1 minus 0, which is the width, times height, or our function value at 0, plus the width of this rectangle, which is 3 minus 1, function value at 1, that's the height, plus 6 minus 3 times function value at 3, plus 8 minus 6 times function value at 6. What's this going to be? 1 minus 0 times R of 0. R of 0 is 1340. So 1340 plus 2 times R of 1. R of 1 is 1190. 1190 plus 3 times R of 3, which is 950. Let's go down. 950 plus 2 times R of 6, known as what's R of 6? 740. That's 740. Summing this up, you get 1340 plus 2380 plus 2850 plus 1480, known as 4 plus 8 plus 5 plus 8. That's going to be 25. So 2, 5 plus 8 plus 16, that's 30. 4 plus 6 plus 8 plus, let me check that again. 3 plus 6, 14. Oh, that's actually 20. 3, 5, 7, and that's 850. And it's going to be, the unit is going to be the liters because it's the amount of water removed from the tank. Now, is this going to be an underestimate or the overestimate? Now, obviously, since we are using the left Riemann sum, the area of the rectangle, the sum of the area of the rectangle is obviously greater than the area under the function. So, this thing is giving us an overestimate, because the area given by this is more than the actual area. It's giving us the overestimate because our function, because R is decreasing, and we are using left Riemann sum, and the left Riemann, R-I-E-M-A-N-N, Riemann sum is used. Now I've included a scoring guide from College Board, and for the part A, you need to have an estimate and a unit, which we do. We have an estimate, negative 120, and we have a unit, liters per hour squared. For part B, you have to have a left Riemann sum, an estimate, and overestimate with reason. Well, we used left Riemann sum, we have our estimate, and we put down whether it's overestimate or underestimate with the reason. So in this case, we got a perfect score for A and B.